Hello everyone, in this video we're going to talk about how to graph our sine and our cosine functions. So far when we've been working with our sine and cosine functions, we've been talking mainly about right triangle trigonometry and most recently the unit circle, but now we're going to go ahead and depart from that and talk about how to graph these functions on the xy plane. And so the first trig function we're going to look at of the two is our sine function. So on these set of axes we're going to work together to graph y equals sine of x. And the way we're going to go ahead and graph our sine function is the way we usually graph a function for the first time we encounter it. And that's by creating a table of values to get a bunch of points that our graph goes through, plotting those points, connecting them, and seeing what kind of shape or graph that we end up with. And so we're going to go ahead and take one trip around our unit circle, use our knowledge of our sine function and its association with the unit circle to generate our list of points. And we have to be careful here. It's easy to mix some things up. Remember, when we're talking about the input and output of our sine functions, we have to be very aware of exactly what we are talking about. The input for our trig functions, like our sine function here, is going to be some angle or arc length on the unit circle, and the output is going to be, when we're on the unit circle, some y coordinate of the point on our unit circle corresponding to that input angle or arc length. And so we start the unit circle at the point 1, 0, but the angle that is associated with that point, or our starting angle, is the angle of 0. And when we're creating these graphs here, our units are going to be radians for our angles because that's what we're going to want to be used to working with when we get to calculus. So for our input initial angle of 0 degrees or 0 radians, the output of our sine function is the y coordinate of that point associated with that angle on our unit circle. And that y coordinate is 0. So our sine function is going to go through the origin. So our next angle on our unit circle is the angle of pi over 6. And the point on our unit circle associated with pi over 6 or 30 degrees has an x coordinate of square root of 3 over 2 and a y coordinate of 1/2. Remember, we are talking about the sine function in this example, so we're more interested in the y coordinate, and that's going to be 1/2. So when our input angle is pi over 6, the output of our sine function, or the y coordinate that we get, is going to be 1/2. And so we've seen the unit circle before, so I'm not going to go through and label every single point over here. This is just to remind us where these values are coming from. Now the x values, or the inputs for our graph that we're going to generate here, are our angles or arc lengths, just like how we had them before on our unit circle, but we're going to eventually plot those on our x-axis, so that's going to be a change for us. And the outputs are y coordinates from points on the unit circle corresponding to these input angles. All right, so to finish filling out this table, I've just gone around our unit circle and looked at these angles that are multiples of pi over 6, right? We still know a few more points on our unit circle, like the multiples of pi over 4, or pi over 4, 3 pi over 4. We're skipping over some of those key points that we found earlier on the unit circle because these points are going to be enough to generate the graph of our sine function, at least the first time around. After we've graphed our sine function once or twice using this many points, we're going to actually end up using a lot fewer points to graph our sine function. But initially, if we want to learn that behavior of our sine function, the more information we have, the more we will know. So one thing we can notice is that the output of our sine function is going to be at most +1, and the output at minimum is going to be -1. So the range of our sine function is just going to be these y values from -1 to +1, which makes sense when you think about the unit circle. The output of sine are these y values from the unit circle, and the y values on the unit circle only go from -1 to +1. All right, so I've gone ahead and set our axes up to go ahead and plot all these points for this first look at our sine function. And to help us here, just for some estimates, remember the square root of 3 over 2 is approximately 0.87. So the first point we're going to have to plot here on the graph of our sine function is 0, 0, or the origin. After that, we're at pi over 6, 1/2. So 1/2 will be right about here. At pi over 3, we're at the square root of 3 over 2, or about 0.87. That's about 0.75, so that'll just be a little bit higher at right about there. At pi over 2, we reach the maximum value of our sine function at +1. And at 2 pi over 3, we start descending and coming back down. we'll go through the square root of 3 over 2 at 2 pi over 3, or approximately 0.87. At 5 pi over 6, we are back down to 1/2. At pi, we will return to 0. Right, just reading our points off our table here. At 7 pi over 6, we go down to negative 1/2. That'll be right about here. 4 pi over 6 will put us at about negative 0.87, or negative square root of 3 over 2. So the next one up is 3 pi over 2, and sine of 3 pi over 2 is equal to negative 1. So we have to plot that point with coordinates 3 pi over 2 for x and negative 1 for y. At 5 pi over 3, we start going back up on the graph of our sine function. So the next output value would be negative square root of 3 over 2, or about negative 0.87. At 11 pi over 6, we return to the value of 1/2, and at 2 pi, we're basically back to where we started at 0. And so now we can very carefully connect these points, and this is always the hardest part for me, but if we do so, we will have the graph, or part of the graph, I should say, of our sine function. And in blue here, we now see the graph of what we say is one period of our sine function. And so our sine function, as well as our cosine function, really all of our trig functions are these examples of periodic functions. A function is periodic if its graph or its behavior repeats itself after a certain amount of time or after a certain length of inputs. And so we generated these points by taking one trip around our unit circle, right? That's how we got these inputs from 0 to 2 pi for x. Those are our angles or arc lengths from our unit circle. Remember, our unit circle, we can continue to take trips around our unit circle. That'll cause our angles just to keep getting bigger, right? After one lap around our unit circle, we'll have gone through the angles from 0 to 2 pi. So if we did a second lap around our unit circle, we go from the angles from 2 pi out to 4 pi. Well, what would happen to our sine function on the interval from 2 pi to, say, 4 pi? Well, we're, again, picking off the y coordinates of those points on our unit circle, and we would get these exact same y coordinates in the exact same order for those x values from 2 pi out to 4 pi. So if we were to extend this graph to increase our interval from 2 pi to 4 pi, say maybe 4 pi is right about here at the edge of the screen, then our graph's just going to repeat itself. And this is just a really rough sketch. It'll look something like this, right? So any interval of length 2 pi is what we say is going to represent one period on the graph of our sine function. And so if we were to go out another interval of length 2 pi further to the right, like say from 4 pi to 6 pi, we would just get this chunk of our graph repeated. And our graph and function would continue to repeat itself and its outputs forever as long as we headed off to the right. And so now if we are heading off to the left, our inputs are going to be these negative x values like negative pi over 6, negative pi over 3, and so on. Well, we talked earlier about how to interpret a negative angle on our unit circle. It just means instead of rotating counterclockwise around our circle like we do for positive angles, for those negative angles, we would just rotate clockwise around our unit circle. And so if we did that, we'd see that we'd still get these same y values repeated, just in the opposite or backwards order. So let's see, 2 pi is a length about that. So that'd be another 2 pi right here. And so if we were to carefully plot the points from negative 2 pi to 0 from our unit circle that are also these multiples of pi over 6, we get this exact same graph showing up again. I'm just going to add a couple little points so my sketch is a little bit more accurate. And really these points that I'm sketching in here are going to be like the 5 basic points that we use when we graph one period of a sine or cosine function. Those points are going to be the points corresponding to like the maximum and minimum on our sine function, as well as these equilibrium or midline points that are kind of the middle or average value of our function. And so here we can see even more of our sine function and its graph. So what we have on the board right now looks like 1, 2, 3 periods of our sine function. Any interval of length 2 pi is going to be one period of our sine function. All right, so now we have the graph of a couple periods of our sine function up on the board. We can go ahead and talk about the domain, range, and symmetry of our sine function. These are some properties of functions that we always want to be aware of, especially when we start doing things like transforming them. All right, so remember the domain of a function is the set of inputs or x values if we're graphing it in the xy plane. And our sine function goes on forever in either direction, so we can input any number or any angle into our sine function. So its domain is everything, the interval from negative infinity to positive infinity, or all real numbers. Remember that Blackboard capital R is our way of denoting all real numbers, or all those numbers from negative infinity to positive infinity. So the domain is everything. The range is not the same. Remember, the range is the set of outputs or y values if we're looking at the graph in the xy plane. And we talked about this before. Our minimum y value is -1. Our maximum y value is +1. So our range is finite. It's that closed interval from -1 to +1. Our sine function also has some very important symmetry that we'll be able to take advantage of at certain points in time. So there's usually two types of symmetry we look out for when classifying a function. That's even symmetry or odd symmetry. Even symmetry is when a function is evenly symmetric about the y-axis. So if you were to think about this being on a piece of paper and you made a crease along the y-axis and then fold the piece of paper in half along that crease, well then, if the graph landed on top of itself, we would say that that is an even function or an even graph. Unfortunately, that is not what happens in our sine graph or with our sine function, but our sine function does exhibit that other type of symmetry. Our sine function is an example of an odd function. So there are a couple ways to define the odd type of symmetry, one of which is a function is oddly symmetric or has odd symmetry if it has rotational symmetry about the origin. So if you take a piece of your graph, like say this piece to the right of x equals 0, and rotate it 180 degrees around the origin, right, the point 0, 0, then it would land on top of the other part of the graph. Well, it's maybe a little bit hard to visualize here, but that certainly happens. If we rotate either piece 180 degrees about the origin, and it doesn't matter which way you do that rotation, it will land on top of itself. So we do have that odd symmetry. Another way to describe odd symmetry is saying a vertical flip is going to do the exact same thing as a horizontal flip would to the graph of our function. So if we flip this graph vertically or over the x-axis, we get the exact same graph that we would if we were to flip our graph over the y-axis or flip it horizontally instead. And that's the one that's a little bit easier to write down symbolically. We say a function has odd symmetry if when we evaluate the function at -x, we get the same thing as evaluating the function at +x, but the output of that function is opposite in sign. So phrasing that in terms of transformations, a horizontal reflection is the same as a vertical reflection. That's what it means for a function to have odd symmetry, and our sine function is an example of a function with that odd symmetry. So we'll be able to use that at some point to help us simplify something or do some kind of algebraic manipulation. And so we can always go back to the unit circle to help us get points on the graph of our sine function and recreate that graph from scratch if needed. But really, in practice, when we're graphing our sine function, the points we're going to use are going to be the points corresponding to the outputs of 0, the maximum output of 1, and the minimum output of -1. And so these points to go through the middle of our graph will sometimes be referred to as equilibrium values or midline or midpoint values. We want to include those. And then also the kind of maximum and minimum values, at least if we want to graph one period of our sine function. The idea is if we want to graph more than one period, knowing what happens to those points and just kind of copy pasting throughout different intervals, we'll get multiple periods of our function if desired. All right, so now we have an idea of what our sine function looks like. We want to repeat this process again for our cosine function, but we won't have to go through all the details and steps together. We still want to generate all those points, plot those points, and sketch the curve, but I'll go ahead and kind of skip through some of that busy work. All right, everyone, so I've gone ahead and generated our table of values for points on the graph of our cosine function and set up our axes to be ready to plot those points. Remember, these points are again coming from the unit circle. The x values or the inputs here are the arc lengths or angles as we travel around the unit circle, and the y values now are the outputs of our cosine function. These are not the y coordinates of the points on our unit circle. These points that we are graphing, the y values of these points, the outputs of our cosine function, are really coming from the x values of points around our unit circle. So let's go ahead and plot these points and see what kind of shape we get. We can notice that we're going through the exact same outputs as we did for our sine function, just with different inputs. So the shape should look pretty similar. These points that we are graphing, the y values of these points, the outputs of our cosine function, are really coming from the x values of points around our unit circle. So let's go ahead and plot these points and see what kind of shape we get. We can notice that we're going through the exact same outputs as we did for our sine function, just with different inputs. So the shape should look pretty similar. All right, so that first point we're going to plot is the point 0, 1. And one thing to maybe notice here is my axes are not set up perfectly to scale, right? My y-axis goes to 1, but if we were to think about how far is 1 on the x-axis, well, pi is 3.14, so 1 would be about a little less than a third of that, right? So my x and y axes are not the same scale here, so this will look a little bit distorted, but we will still get the general shape and behavior of our cosine graph. So that first point is 0, 1. Our next point is pi over 6, square root of 3 over 2, or about 0.87. After that, we are at pi over 3, where we have an output of 1/2. I'm not labeling all of our x values here, just kind of the more important ones. That'll make it easier to see our graph, I think. The next point we're going to plot is pi over 2, 0. And we're all pretty familiar with plotting points, so let me go ahead and speed through the rest of these. All right, so this is what our points look like when we go ahead and plot all 13 of them on our xy plane. Now, if we carefully connect these dots, we get the graph of our cosine function, or part of the graph of our cosine function. So just like our sine function, our cosine function is going to be periodic and repeat itself after we take a trip around our unit circle or over every interval of length 2 pi. So this is what one period of our cosine function is going to look like. If we were to copy paste this over to another interval of length 2 pi, then the graph would just repeat itself and look something like this. So I drew that one very quickly. Let me be a little bit more careful with plotting some extra points to graph an additional period of our cosine function, but now to the left of x equals 0, or for these negative x values. Remember, we can still get these values from our unit circle. These negative angles we just interpret as traveling clockwise around our unit circle instead of counterclockwise as we do for these positive angles or inputs. And also, just like before with our sine function, in practice we do not use nearly this many points to actually sketch a part or a period of our sine or cosine function. We really only use 5 key points. So for this additional period, for these negative x values, I've gone ahead and used those 5 key points. They're the points corresponding to the maximum output of 1, the minimum output of -1, and these equilibrium or midline or average values of 0. And so now we can see at least 3 periods of our cosine function graphed on the xy plane. Notice it does have that same shape as our sine graph, as we expected, through that pattern of outputs for very similar inputs. The difference, if we were to look at them side by side, is that they really are just kind of horizontally shifted versions of each other. And so let's go ahead and have that same conversation for our cosine function that we did for our sine function. Let's talk about the domain, range, and symmetry our cosine function exhibits. So let's start with the easy ones, the domain and the range. The domain is the set of all inputs or x values that we see on our graph here. And remember, our graph continues repeating this behavior forever. We can go as far as we want in either direction with respect to x. So our domain is, again, all real numbers, just like it was for our sine function. And the range is also going to be the same as our sine function. We do get those exact same set of outputs, just in a different order. Our range are all these y values our graph hits from -1 to +1, including those endpoints. So our sine function, remember, had that odd symmetry. It had that rotational symmetry about the origin. Our cosine function does not exhibit odd symmetry. It exhibits the other type of symmetry, that is that even symmetry. Right, I may not have drawn it perfectly here, but if I did, then the y-axis would perfectly cut our graph in half. If we were to fold our piece of paper or our graph in half with the y-axis as the crease, then the two pieces would land and basically kiss each other or land on top of each other. So our cosine function certainly has that even symmetry, and we can also express that even symmetry symbolically or algebraically in the following way. We would say that cosine of -x is the same as cosine of +x. So another way to interpret that, kind of thinking of transformations, is a horizontal reflection of cosine is the same as the original cosine function, saying if you flip this graph horizontally over that y-axis, nothing happens. You're still working with the exact same version of your function.